We have just started our chapter on quantum theory and atomic theory, and we are now beginning, we just finished cavity radiation in section 39.1. We're now going to look at section 39.2, what is called the photoelectric effect. Now, what is the photoelectric effect? Well, it turns out that if we take a piece of metal and we shine light on it, electrons will bounce out. Well, that kind of makes sense. Metals like steel or copper have extra electrons in their outer shells, and if we put energy in here, we get electrons that are going to be knocked out because of their energy. So that makes total sense. Turns out that this energy has to be kind of intense. It has to be not in the visible light, but it has to be in ultraviolet light that we get this effect. Well, it turns out that this led to all kinds of problems as people began to study this. How did they study it? Well, they studied it by putting a collector up here and made this collector positive. They made this plate negative, and they were able to put a grid across here, and they could adjust the voltage here so that by making this very positive, these electrons would flow rapidly, and by making this grid here where it was negative, the electrons would be pushed away and not flow. So they could study how much energy these electrons had and how that varied with the light. And as they were studying this, this is called the photoelectric effect. Photo from the light, electric for electrons. They found some really strange things. It turns out that the energy of the electrons is independent of the light intensity, but it depends upon the frequency. Well, that's as bizarre as anything can be, because we know that if we have more energetic light, this amplitude would be bigger, and we'd have more energy, because you recall the energy was equal to the square of the electric field plus the square of the magnetic field. It's the amplitude squared that gives us our energy. So we get brighter light, gives us more energy, but it turns out that the energy of the electrons doesn't care. How is that possible? Now we get more electrons, but the energy of the electron depends on the frequency. So this is not true. Energy does not depend upon the amplitude, not proportional to the amplitude of the light. No, the energy is proportional to the frequency of the light. Well, why would it care what the frequency is? Now, it even gets worse. Below a given frequency of light, if I make that frequency smaller and smaller, at some point no electrons are emitted at all. It doesn't matter how bright the light is. I can take light and shine it on this metal that will almost melt it, and not one electron will come out. How is that possible? So there's a threshold. No electrons below a certain minimum frequency. Well, things are getting weirder and weirder. The effect of emission is immediate, no matter how low the intensity. What do we mean by that? That means that if we were to take a candle way out here, or a light that's so dim you can't imagine it, and it's so weak, and it goes for 50 miles and goes over here in this plate, you can compute that it would take hours or days for enough energy to get over here to knock even one electron out. But if that light has a frequency greater than that minimum, then it turns out the electrons come out immediately. How is that possible? There's not enough energy there to do it. Well, these problems were counter to Maxwell's theory, and all of Maxwell's theory, with its constancy of the speed of light, was what Einstein used for the theory of relativity. The results of cavity radiation was certainly counter to the Maxwell theory. It was Einstein, working at the same time as he was developing relativity, that explained both these phenomena And he basically, along with Planck, founded the concept of quantum theory by postulating the existence of a photon. What is a photon? A photon is a quanta of light. Up to this point, the Maxwell theory dealt with light as oscillating electric and magnetic fields, which went perpendicular to one another. And Einstein said, no, that's only an approximate theory. Light is really made up of quanta called photons. These photons have no mass, but they do have a frequency and a wavelength. They have energy and momentum. How much energy? Well, it's not like Planck said. It's not that the in our last section, that the walls of the cavity only emitted and absorbed certain frequencies. It's that the light itself inside the cavity only had those frequencies. And you could see how he derived that. If you just look at the data, it says energy is proportional to frequency. Well, let's just take what it says and believe that. And so he said the energy of the photon is proportional to the frequency. And he said the constant of proportionality is Planck's constant. One of the most important equations in physics. It defines the energy of a photon that has light of a given frequency. So he's saying when light has this frequency, it exists in little packets. These packets are indivisible. They're called photons. They have no mass. If they have a given frequency, they have this energy, no higher and no lower energy. And therefore, Maxwell's theory is wrong. Now this is so remarkable because Einstein had just used Maxwell's theory and said it surpasses Newton's theory and used it for the constancy of C. But he didn't use these other aspects of the Maxwell theory and assumed that it was true. So energy electromagnetic is H, which is Planck's constant, times the frequency. And the light of these quanta are purely massless particles. And you recall that our equation previously was E squared over C squared minus P squared is equal to M squared C squared. But for a photon, there's no mass. It travels at the speed of light. Therefore, it follows that E over C is equal to P, or E over C is equal to P. And so now we can figure out what P is. They must have a momentum, which is H over F, H over the frequency, divided by C. But now you will recall another equation that holds for all waves that says wavelength times frequency is the speed. Therefore, if I divide both sides by the frequency, I would get what? I would get wavelength is equal to C over F, or F over C is equal to the 1 over the wavelength. Therefore, this F over C is 1 over the wavelength, so P must be equal to H divided by the wavelength. And this is our other equation. Remember, that comes from this special equation, which is always true, and the Einstein relationship between energy and momentum when you have no mass. And if I combine those two, I can now say photons have an energy which is proportional to the frequency and a momentum which is proportional to the inverse of the wavelength. These are two of the most important and crucial equations in all of this this work, certainly for quantum theory and serving as its foundation, but also for the entire course on physics. So now our view of electromagnetic radiation is more sophisticated than oscillating electric and magnetic fields. That's just an approximation, and actually those fields consist of trillions and trillions of photons moving along, and that gives the impression that we have these oscillating electric and magnetic fields. This was done by Einstein at the same time he did the special theory of relativity. Absolutely remarkable. So the theory, our quantum theory, was begun by Planck and then taken up with the photoelectric effect by Einstein resulting in these two equations for light, or photons.